So here's part B. We need to solve for the value and also units for K. So there's actually two ways to do this. You should be familiar with both of them. We know it's second order based on the R squared value of the 1 over concentration versus time graph. So here, this is y is equal to mx plus b, and m is your slope, and for second order integrated rate law, the slope is equal to positive k. So our value for k is 0.0561, and we get that because it's our slope. Another way to do it is how you're kind of used to doing it, and that's substituting into the second order integrated rate law. So the second order integrated rate law is 1 over concentration of A, in this case our A is BRO, minus is equal to K times T plus 1 over the initial concentration. Okay, so if we're going to sub things in, we just have to pick a point. I chose to pick the first point, so that's going to give me, that's not true. I chose to pick the point at 40 seconds. So we're going to have K, our time is 40 seconds. The initial concentration is whatever the concentration was at 0 seconds, so that was 0.750 molar. And then at 40 seconds, our concentration was 0.280. And then all you do is algebra in order to solve for K. So when you rearrange the equation here, K ends up equaling 0.0560. It's off, in the third sig fig, but I would accept either answer. To get my units, you're going to have reciprocal molarity because of what you have here is 1 over molarity. You'd be subtracting 1 over molarity, right? So you have reciprocal molarity here is equal to K times seconds because our time was in seconds. And then you need to divide both sides by seconds, okay, over 1. And that would give you K has units of 1 over molarity and seconds. So you can either write it like that, or you can say molarity to the -1, seconds to the -1. So then we can just add those units to our K values. To solve part C, we're just taking our equation, okay? This is the second order integrated rate law. We have substituted in our K value with units, but we're given a T in the problem, right? So our T is 10 seconds. Yes, our T is 10 seconds. All right, so we put 10 seconds in here. We have our initial concentration. That's just at time 0. What was the concentration of the hypobromite? So it was 0.750 molar. All right, and then we're solving for this. This is our X. So the algebraic manipulation, once you do it, you will get X, which is equal to our concentration of hypobromite ion at time is equal to 10 seconds. That concentration is 0.528 molar. So that's how you do part C. Anytime you're given a certain time and you already have the integrated rate law with K in it, it's an easy plug and chug. Okay, so now we have to find the half-life for part D. Recall that for half-life, it's defined as the amount of time that it takes for the concentration to become 1/2 the concentration initially. All right, so this is always going to be true at your half-life, which we can represent as T sub 1/2. So here I just have the second integrated rate law. I am going to add a little 1/2 so that we know we're talking about the half-life, and we're actually solving for the half-life. So that's our unknown. We have all the other info here. So again, our K value is 0.0561. Then we have our half-life, which is our unknown, plus what was your initial concentration? That was the 0.75 molar. And then what we're doing out here is we're figuring out the concentration at the first half-life. Okay, so that's just going to be 0.750 divided by 2, okay, when it's cut in half. So out here, we're going to have 0.375 molar. And again, you're going to do your algebra. You're going to be able to solve for T, and that specifically is your half-life. And the reason for that is that we took initial concentration and then we cut it in half. So that means you'll automatically be solving for your half-life. And when you do that, you get 23.8 seconds. In order to get that, I think I used 0.0560. So if this is 1 decimal off, don't worry about that. So do recall that for second order, half-life is not constant. So we can't say for every 23.8 seconds, you'll always, cut in half your concentration. That's only going to be true for first order. All right. So if we wanted to figure out the half-life for this second order reaction at another point where we were defining a different initial concentration, it's not going to be equal to 23.8 seconds. People can get tripped up on that.